Okay, just give it a little moment here. Let people get in. So this is my first webinar for the Danish Sound Cluster after my maternity leave. It's very nice to be back, and we have since gotten a huge office and 4 more team members and a logo, acoustic panel with a logo on it. So yeah, a lot has happened with us in the Danish Sound Cluster, and it's really nice to be back. And also good timing because Pedro, who has been hosting the webinars when I was away, he is speaking today. So nice that he doesn't have to wear both hats at the same time. And yeah, welcome to all of our listeners today. I think, still some people joining, but we'll just get started. Yes, so we're here today to learn about what's new in the world of haptics and bone conduction technology. One of our speakers, Vincent Hayward, he's the professor of tactile perception and one of the co-founders of Actronica. He is unfortunately ill and not able to join us today, but we do have some of his links to his work and some podcasts, so we'll send you those afterwards in the follow-up email, and hopefully he can join us another time. But we have 3 brilliant speakers, so welcome to Pedro, Claire, and Gabriella, who will present to you today. We're going to be recording the webinar, and we can share it afterwards, or we will share it afterwards on our YouTube channel and on our website. And we're also going to send you the slides, so you don't need to take screenshots along the way. If you have any questions, you can click on the Q&A chat in the bottom, and please just write your questions throughout so you're not so you don't forget them, and then we'll take them all at the end after the presentations. I think that's right. Oh yeah, before we jump in, we have a poll. We have a poll today. So I will just launch it. So you can just take a moment to answer these 2 questions. We just wanted to know a little bit about who is joining us today.
Oh, I'm not sure it's working, actually. Is it working?
Yeah?
I can't select stuff.
No, you're not allowed to answer.
Oh, yeah, that's right.
I'm assuming you do know something
yeah,
about
but the
bone
window
conduction.
still pops up and it's like tricking me to press.
No, you just watch the poll.
I was like, yes, I've heard about bone conduction before.
And I didn't think the sound quality was very good. Yeah.
I want to bias the results.
No, your opinion doesn't count.
Totally.
Oh, good. Okay, so we can see that most people actually have tried a bone conduction device or product. That's cool.
That's great.
We have the experts with us, so that means you guys can get really nerdy and into the details. Okay, some people liked it. 36% of people liked it. Can our audience see the poll? No. The results?
So what?
Can our audience see the results?
I don't know, actually. I've never tried this before, so it's the first for me.
Yeah.
So you can just say it. So I can't see it. So
okay, so most people, 83% of people have tried a device, and
Carsten
some
says
people.
No, so
Okay,
yeah.
Most people said it was reasonable, or let's say, what is that? 70-something% thought it was reasonable, or they quite liked it. So maybe they're not as picky as you and I, Pedro, but we are not fans of most bone conduction headsets on the market. All right, but with that in mind, I'll let you take it away, Pedro. Pedro's going to do the first talk.
All right, I'll just share the screen and you can spotlight me.
I shall, yes.
Oh, just a second. Is that good?
Yes, that's great.
Perfect. All right. So welcome everyone. As Shelley said today, I have a bit of a different role. I was invited. So here I am with another hat, and I'm gonna talk about my actual the business that I have founded. We do bone conduction. So I just would like to start by saying that please be open. There's of course a metaphor to this, but also open-minded, because I think it requires some open-mindedness to think about these other types of technologies that are different than the standard stuff that we're so used to since we exist. So yeah, just be open. So I would like to also start by introducing myself, because I normally don't take that much time to say a bit about me. So this is a good opportunity for that. So yeah, I'm the founder and CEO of Oracle. And I like to see myself as I have Portuguese roots, but I have Danish branches. I've been here for quite a few years. I really love this country. So this is a bit of a background. I actually play music since I was 7 years old. I started playing piano, and then guitar, bass, singing. But I'm a bit of a hybrid species, because I was born with a hearing loss. So ever since I remember, I've just been completely obsessed with understanding hearing and understanding sound beyond do, re, mi, fa, sol, like kind of making some sense of it. And I remember specifically like a music class where the teacher introduced frequencies for the first time, and finally I could put numbers in notes, and that was just a revelation for me. So yeah, I ended up, of course, dedicating my entire life to sound, and I studied in DTU like so many of us. And then after that, I worked with hearing aids. I worked with regular air conduction hearing aids. I worked with bone anchored hearing aids, which is the surgical vibration, bone vibrating surgical hearing aids. And I also worked as a consultant for a few years, doing several different things. So yeah, I think it's, even though we could see in the poll that a lot of people know what bone conduction is, but I think it's still worth talking a little bit about it, in case there are some people who don't know. So as the words indicate, for the most part, we have air conduction, which is sound going through the ear canal and reaching the eardrum, and then vibrating the middle ear bones and then the cochlea. Bone conduction basically bypasses some of this system by vibrating directly on the skin and bone. I would also like to make a small remark here, but Gabriele will get more into the details. But basically, bone conduction is actually a very conventional term, but it's also a bit contradicting, because actually it's more correct to say that we do cartilage conduction or soft tissue conduction, because actually we are vibrating, we are more relying on the signal path that goes from the skin rather than only the bone. But I won't get into many details. So this is mainly the difference. And I would like to make you guys think about, like, why is it important to be open? So I have a few slides that kind of try to explore this. So it's very broad and very abstract. But first of all, like, for example, on the left side there, you have the typical over ears, which is what I'm wearing as well. And these headphones, they're more than 100 years old, actually. This is such an old design, and it's something that we're so used to that we don't really question it, and also because it sounds great and it's been improved over the years. But the fact is that this is a very old invention, with the progress of technology, we have come up with other stuff, right? And that's like the stuff we have on the right, which is the in-ear stuff, and the in-ears They are great as well. So they still stimulate air conduction in the ear canal, but they have like normally a massive issue for a lot of people, which is the occlusion effect. And the occlusion effect, for those of you who don't know, is basically when you clog your ear canals and then you have this sense that you're occluded. You hear the occlusion, like when you walk, you hear your steps. When you chew a cracker, you hear the cracker. And this is very disturbing because it's so loud. So why be open? I mean, first of all, innovation, is important, and rethinking things, and for a lot of cases, people don't want occlusion. So that's clearly a very good reason. So, but then we have other types of use cases. So, for example, as you guys have heard for probably the last 4 months or so, or maybe less, AI has just been polluting every news feed, 90% of it. And it's just, so I hope that some of you guys have seen this movie. It's called Her. And it's basically Joaquin Phoenix. I don't remember his name in the movie, but he goes through a divorce and he buys these headphones that have actually AGI on it, and then he starts talking with this every day, and he falls in love with this AGI. But the tricky part for me as an acoustician and a designer, it's like, why is he wearing those in-ears? And this is kind of a little bit in the future, but then this hardware piece is so old school. And is he really gonna be talking every day all the time with this AI and be occluded or be completely not aware of his surroundings? Or so I would think that in the future, if we were going to talk with the AI all the time, we want to be open so that we can talk with other people at the same time and even use the AI together. So I think there's a lot of possibilities here when the mix between being open and the AI. This one is actually the current, you could say, business model, or the current value proposition that we always focus on, because obviously for some use cases, you want to remain open, because if you're biking and you're wearing headphones, you could run into a car because you don't hear it. So this is one of the most obvious use cases. So if you have your ears canal open, then you can pay attention when you're biking, when you're running. So basically something that the danger could come quickly, something in the move. And I think the last one I've added up that is very interesting with bone conduction, which people don't necessarily think that much about, but is actually another topic that's going to come with Claire. But bone conduction, because it's vibrating on your skin, actually has this extrasensorial stimulation. So it's not only the sound, but you can actually feel the vibration, especially at the low frequencies. So some people even describe it, for the first time they've tried it, if you have enough low frequency and if you do it the right way, then some people describe as it feels like I'm in the concert, because that's what it resembles when you feel the bass in your body. It's like you're feeling the music, you're in the concert, just like with the big subwoofers you have in live gigs. So this second group of slides, I'm thinking more like the skeptical. I went from these is all the good things about it, and now I'm gonna go like try to remove the fallacies. So open, what for? We have transparency mode. And yeah, I do believe that transparency mode is really great for some things, especially if you're indoors. But the moment you get out, like if you go on a bike or even if you're walking and it's windy, transparency mode, it's not so transparent anymore, because the wind takes over and the microphones love wind and the algorithms are still not that great at it. So I'm not sure when this is going to get fixed. It's not an easy challenge at all. So that's number one. Transparency mode does not work with wind. So obviously, if you go biking, And then also when you wear this kind of stuff, over ears or in ears, you're actually not wearing your pinna. So if you don't wear your pinna, you lose a lot of the localization cues. So you can't tell as much where the sound is coming from. So that's also a pretty dangerous thing if you're biking or on the move. And then, of course, the last one is occlusion remains, and ear canals are still stuffed with foreign objects. So it's something that really annoys a lot of people, even with transparency mode. So then open for what? Bone conduction has bad sound quality. So this one I've heard so many times, and I am answering sure in the 80s. Of course, there is still a lot of, like you just mentioned, Shelley, there's still a lot of bad sound quality bone conduction out there. I don't think, like, I'm biased, of course, because I'm making one. But I'm pretty sure this is not a problem anymore, and we have solved it to a large extent. And don't listen to me, go check our testimonials, talk with people who have tried it. So yeah, just like other technologies that didn't work for many years, but now they do. So yeah, and the way we do it, of course, I can't tell you because it's secret recipe. But I'll quote Aristotle here. He says the whole is greater than the sum of its parts. So it's not, it's not one thing or two things, it's 4 or 5 things added together. So all the, the acoustics, the electronics, the digital part, the mechanics, the everything counts, and added together in the right way creates good sound quality. So, and then this one is more thinking about hearing, because what for? We already have open domes, and open domes, again, a lot of people that fit hearing aids with open domes, their adaptation is much faster. It's really great, but it's not a perfect solution, because first of all, they're not completely open. You still have an object inside of your ear canal. And then there's a lot of challenges with feedback, because you have complete leakage going from the speaker to the microphones, and it's an open dome, and they're both air conduction, so there's a lot of feedback problems. And of course, because the dome is open, then you are not using the resonance of the ear canals, so you have more leakage. So the low frequencies are actually, so that the resonance frequency moves up, and you have problems in the low frequencies. You have to boost them a lot, basically. And that could be a problem. So this is just a little journey, and I like to put the silly one on the left, because that's where it started. It looks ridiculous, but that's where we started in the beginning. We had this kind of ring around the ear, and we basically put the system in that ring. It didn't take me long to realize that was a bad idea, and then one day I was like thinking, because I wanted to be in the tragus area. There's a lot of good reasons for that. I can tell you later if you want to ask in the Q&A. But to be in the tragus area, so then I thought, okay, maybe I just want to focus on that area. I also don't want to focus on the top, because I don't want to have glasses and hearing aids and headphones and hats all hanging in the ear. So then I came up from the clothes spec, basically the hanging for the clothes. I looked at that, I was like, oh, that could work. And of course, it was a terrible idea, because it hurts a lot when it's very tough, but it worked. It was the beginning of the idea. And then we did so many iterations, and now we have a very comfortable version of the clamp system. Or yeah, we have several names for it, but I'll show you later. So this is what I'm talking about. It's patented. We call it the attachment means. That's just the patent term. So it is a clamping system, and it clamps to the tragus. There is acoustical reasons for that, and other reasons, and it's comfortable now. And yeah, that, I mean, the GIF pretty much explains it. This is very different from the competition. The competition is a fitness band that goes on top of the ear. So what we have is actually a coupling system where you can couple with the tragus, because the tragus is nothing more than a piece of skin that is resonating. So if you harmoniously move it, as opposed to coming down with the other way, which is basically contact, and it just hits like that. So if you have a lot of displacement, for example, especially in the low frequencies, that could be a problem, and it creates more tickle actually. So this way you keep a good coupling, and then in the beginning you have 3 there, so you can fit 3 different sizes, so you can just basically take it out. And for different years, you put different sizes. So that's how it looks. That's the first version. That's what we're working on. It's a Bluetooth device, of course. It's a headphone. It has capability to do different kinds of DSP. It has bone conduction transducers, obviously, customizable tips, and we have a patent. Yeah, so I'm sure some of you already seen this before, but we did a crowdfunding a while ago, and we pre-sold close to 500 units. So that was a success story. We are a team of 6 people. These pictures are a little bit old, but yeah, so we have people in acoustics, DSP, design, electronics, and software development. I put up there startup jugglery because it's really a juggle. It's a juggle. But yeah, so right now we are solving the final issues we have with late development and starting the production. So in 6 months' time, we'll be in the market and finally deliver the 500 units. And just to have a little bit of a, since there's so many good people here, we're actually looking for collaboration partners, both in the industry and in the academia. It can be within sound, but it can also be in other areas that complement what we're doing, and genuinely also people who are just very interested. I mean, we're always open to talk with just about anybody, except for marketing services. We're not interested, but other than that, it's fine. So I wanted to leave this presentation with like a cliffhanger, because I think it's super important. Because even though in the beginning we're still only focused in bringing it to the consumer market, to the awareness, to the user that wants to be aware and all that, I think it's very important to recognize that that nowadays, or for many years, we have developed all these amazing solutions for people that have sensorineural hearing loss. So we provide a solution through air conduction, and we have countless. There's so many, but the problem is, yeah, okay, there is a lot of people needing that, but there's also a lot of people that need hearing amplification or hearing loss compensation through the skin and bone. And it's actually, when you look at the numbers, this is the last time I checked. I don't know if it's correct anymore, but I mean, 150 million versus 250 million. I mean, the numbers are not massively different. And of course, the 150 million also includes mixed hearing loss, so it's not only conductive. So this is something to think about, because this kind of technology is actually still, there's a lot of room, and there's a lot to be done. So if you're watching this and you're working with hearing, go talk with your boss, and maybe come talk with me afterwards. I mean, I really want to contribute in this way, and yeah, let's work together, basically. Yeah, stay open. So that's it. Thanks.
Thank you, Pedro.
You're welcome.
You're welcome. Yeah, I hope you get some partners from the audience. I didn't know that 150 million people.
Yeah, I have to check the numbers again. This is a little bit old, but I mean, it's so many people that need, and these people right now, they're served with air conduction stuff, which is fine. But if you think about it, if your eardrum doesn't work well, or if your bones, middle ear bones don't work well, then you're only serving them partially, right? So yeah.
Yeah, I have a lot of questions for you, but I'll save them for the end.
Okay.
Let's move on to Gabriele,
Cool.
who has worked with Pedro and is going to speak about his project. Are you ready to share your screen?
Yes, I am.
Wonderful. Take it away.
Remember the spotlight thing.
Can you hear me and see my screen? Okay. Yes. Cool.
Sorry, I muted
Perfect.
myself. I
Yeah,
can
no
hear you.
problem.
All good.
Yes. Hi, everybody, and it's great to be here. Thank you for inviting me. Today I'll be talking about basically what was a collaboration between DTU, the Danish Technical University, and Oracle. That goes back more than a year ago now. When I first met Pedro, I was looking for a master thesis project, and we had a chat from the very first time we talked. It was clear that there was something to it, and they would like to collaborate on the project I'll be talking to you about in just a minute. As Pedro did, I'll just give you a very brief presentation of who I am. I have I've been studying in Italy, a bachelor at Polytechnic School of Turin, moved here in 2020, middle of COVID time, to follow the dream of becoming an acoustic engineer. DTU ended up being a great opportunity. Learning, it was a great experience, and getting to the end of the 2 years masters, then I decided to go with the project with Oracle, and today I'm working in the audio industry at the Force Technology as a sound quality specialist. And yeah, we're benchmarking audio products as I wrote here, and it's still in the perceptual studies field, which is I'm also very grateful for. Um, so getting into the main topic of the thesis, this is the title of the thesis. So it was evaluation and modeling of subjective multisensorial perception in bone and air conduction technology, which might seem like a very long title, and on the one hand it is, but we'll just go bit by bit in this presentation. So I developed the interest in the field of bone conduction headphones during the masters. As I said, the technology behind these headsets are often commercialized with the name bone conduction headphones. But the technology behind it, and we could say the discovery of the auditory pathway, was only found in 2004 in Japan. At the moment, there's not an established method to measure the performance of the bone conduction headphones. So we don't have a clear way of getting out data and having reliable data. And this is thus not ideal, since in the past, as Pedro was also introducing, we've had this poor sound quality reputation of bone conduction headphones, and particularly in the low frequencies where the most problems are usually concentrated. And thus, my thesis investigated how and if it was possible to measure the performance of such devices, and also in comparison with air conduction, which is obviously the main mean we use to listen to music. So I started from searching on Amazon for bone conduction headphones. So this is what you would get out of Amazon.com if you look for bone conduction headphones. But actually, scientifically speaking, if we're looking at this, these are not bone conduction headphones. So this is the name we give to them, but bone conduction is actually a slightly different thing. We call this cartilage conduction. So this illustration, I believe it's pretty nice to understand the difference here. So we have obviously air conduction. You see it here in light blue, and then it's the obvious pathway that we most likely all are familiar with. And then we have bone conduction transducers, which are the ones, for instance, used in pure tone audiometries to look into the mastoid response that we get. And so that would be like pure bone conduction. In the case of these headphones, we have somewhat in the middle, and that's also called third auditory pathway. There's literature that's been backing up the cartilage conduction as a third auditory pathway. And I have another illustration in just a minute that will explain how we try the contributions to cartilage conduction. But let's just start from the idea that these headphones that we have at the moment on the market that basically look into the response that we have here in front of our ear canal on the tragus area are not bone conduction. They're not pure bone conduction. So here I included a couple of characteristics of cartilage conduction. We have the vibration that's driven into the oral cartilage. The sound information, including speech, is perceived with the same precision when that is when it's transferred through air conduction or bone conduction. We found the tragus to be the best placement of the transducer. Also here we have multiple literature studies looking into the difference of different locations for a transducer. And we've seen that the tragus right here in front of the ear canal is the best place to drive the signal. And the loudness of the sound is directly proportional to the pressure between the transducer and the cartilage. And this is different than bone conduction. So here we look at some more detail into how cartilage conduction signal is then driven into the skull. And there's three main pathways that we can have. You have here, number one in orange, which is just cartilage bone conduction. So the signal is driven into the cartilage first, then we have the transfer of the vibration into the bone, and then from there into the inner ear. Then we have the green pathway, the cartilage air conduction. So it starts in the cartilage, and then the cartilage part of the ear canal is vibrating, and part of that sound information is then transferred into the ear canal and goes through the tympani. And then we have direct air conduction. So basically that'll be part of the sound that's just leaking into the air and then getting into the ear canal the conventional way. So we've been investigating this. There's different studies that try to investigate this. It's not 100% clear the precise percentages that we have on each of these contributions. What we do know is that most likely number two is the dominant pathway. Then we definitely have some contribution from 1 and 3 as well. So with these premises, you could ask why looking into this problem perceptually. As mentioned in the title of the thesis, what we try to do is looking into the perceptual side of this topic. And the reason is that the mastoid simulators that we have at the moment are not reliable. Here I'm showing a plot from a study. This was a loudness matching study that was performed. And here we see curves that were perceptually measured. Here you see the black one and the black dashed one. These are the ones that were perceptually measured. And then we have the gray one with a coupler. And as you can see, it wasn't really aligning very well. So we can conclude that it's not that easy to simulate how our skull is responding when we try and drive such vibration sound, such sound information into it. And so this is the reason why we tried to develop a method and try to see if we could get reliable data out of it. So here's what we did. We developed a MATLAB interface to perform the experiment. So the MATLAB interface was built in order for us to have a reliable mean to gather data, and also, of course, to play the stimuli and to give the assessors the opportunity to have something to look at and to guide them through the experiment. We had 20 normal hearing subjects aged 19 to 33. They were all screened prior to the experiment, and we had a maximum asymmetry between left and right ear equal to 5 dB HL. And we decided to keep this parameter pretty strict. I had some previous studies that had like a 10 dB asymmetry as their limit, and we decided to bring it down to get as much reliable data as possible. We had a calibrated Sennheiser HD 650 open back headphones on the left ear as a reference for all test participants, and then the tested device on the right ear. And we had a reference level of 85 dB SPL played by the HD 650. We had stimuli generated through MATLAB that were played between 70 and 2K, 2000 hertz, both on the reference and on the tested device, and they were alternating. The user was able to see this alternating stimuli on screen and at the same time experience it as they were hearing. They had a knob in front of them to adjust the loudness of the tested device to the loudness of the reference device that we're wearing on the contralateral ear. And then on top of that, as you can see on the right, in the bottom part of the image, we had a vibration assessment to look into how much vibration the assessors were experiencing during the listening test, and also a sound quality similarity assessment. So basically, we wanted to look into, okay, maybe they can match it, but how is the sound quality of that? Is that similar to what they're listening in the reference headphone, or is that something completely different that might be distorted or it might have some trouble in the way getting into their perception, on the way to the brain, basically? We had 3 tested devices, 2 cartilage conduction ones. The first one is Shock's Up and Run Pro, is one of the latest models of this company that does actually has a lot of different models. It's this design with this little arch that goes around the ear, and then it sits right in front of the ear canal. And then we did the auricles, which Pedro gave us a pretty good introduction about, and then we had this Sony WH-1000 XM4 is kind of like a pretty popular consumer super ear pair of air conduction headphones. So looking at the results we got, basically we had different data points, as you can see here, ranging on the x-axis between 70 and 2K. And then on the y-axis, what you see is dB full scale that were needed, the signal that needed to be sent into the different devices in order to be able to match the reference of 85 dBSBL. What comes out quite clear in the beginning is that we have the air conduction device that perform better. Here, you could say that in the top area of the plot means that a lower amplitude of the signal was needed in order to match. So there was some headroom, but as you can see, going up in frequency, then both the air conduction and the cartilage conduction devices aligned at a 2K. Actually, we have data points that are quite overlapping. It was also very interesting to see that there was a difference between the 2 cartilage conduction devices. We looked into this also statistically, and we found significant differences between the 2 devices at 3 low frequencies. So here you can see 70, 100, and 250 hertz. We were pretty interested, and we were actually pretty looking forward to seeing these results, because they confirmed there was a difference between the devices, and that we could measure reliable data out of the experiment that we had built. At the same time, we had results from vibration. And it's interesting to see that, of course, the air conduction device does not have vibration as one of its core features. So as you can see here, some people reported some slight vibration at low frequency, but that's definitely not the core of the data that we see on this plot. The core of the data is observing that the 2 cartilage conduction devices had results that were quite similar. That was interesting to see, because we know by literature, by studies that have been made, that vibration can enhance the perception of loudness. So it's been shown that if we experience a vibration at the same time as a sound, we perceive the loudness of that sound to be higher. And it's interesting because the vibration that was reported by our assessors in the 2 cartilage conduction devices were not that different. They were actually aligning pretty well. And that gives more backup to the difference that we saw into the 2 devices in the loudness. So as you could see, going just back one slide for a second, as you can see here, there were some differences between these 2 devices. So we were looking into, okay, maybe there might be more vibration in one of the 2 ones, and that might enhance the loudness that the assessor have reported. But then when we look at the vibration, we're like, okay, they're actually quite aligned, and this is pretty interesting. It gives and adds information to the first results. Then we had sound quality similarity. So here we had a question. We were asking the assessors to rate how similar it was, the sound quality of the tone they could hear on their tested device compared to the reference, basically. And they reported them to be quite similar to the air conduction device and a little bit different on the bone conduction devices. This could have multiple reasons, and we couldn't investigate more in this study which are the reasons why the sound quality similarity was different. What can be highlighted by this data is definitely that the cartilage conduction devices had the two of them had similar results. People reported them to be slightly different than the reference, but for sure there's a vibration component that we mentioned before that is highly correlated with this probably as well. So it's a very different experience. And in the poll in the beginning, if most of you have experienced using a bone conduction device before, then you know it's quite a different experience. It's quite a different thing in terms of perception than just using an air conduction device. So definitely it would be very, very it would be great to have some more time to study how the sound quality can be studied more in detail regarding bone conduction devices. And so yeah, we just had this time during the thesis, so then at some point we had to stop, and we were looking into different topics as well. We were interested in looking how we could use, for instance, this device with speech and noise tests and trying to assess different characteristics of it, but that'll probably be for the future. And yeah, so I'm done with my presentation, and thank you for listening.
Thank you, Gabriele. I know we said questions at the end. Oh, but just as you had your, could you share your screen again? And we can just take one of them now. Or maybe a couple.
Sure.
Karsten was asking if you can explain what sound quality difference is. The dB scale.
Yes. Let me just get back to it in a second. Can we go back here? It's not responding.
Yeah, I think what he means is the scale itself. Why did we use dB scale for the sound quality?
Oh, I know what it means. I just saw it. Yes, that's not dB full scale. That's a typo. It's not the dB full scale. It was a rating that the assessors would give on a scale from 0 to 100. So that's just a typo in the plot. And thank you for noticing. Correct. That's great.
It's always the way. Okay, we'll come back to the other questions.
Thank you very much.
Later. Thanks a lot for your presentation. And now we have Claire Richards, who has just completed her PhD at IRCAM, and she did a presentation for us in December 2021. So it's really nice to have you back, Claire, and congratulations on your PhD. And yeah, what's interesting about Claire is she's not an audio person originally, but she comes from a design and perceptive sciences. Is that what it's called? Approximately perceptive sciences background, and studies in ergonomics. And she also has hearing loss herself and then moved over to working with haptics. So I'm looking forward to hearing an update on your work.
Thank you for the introduction.
course.
I'm gonna figure out my screen sharing real quick. All right, so if I do this, nope. All right, and then this will just be a second.
Looks great
for everybody.
Yeah, looks good.
Okay, cool. So hello everyone, my name is Claire Richards. I'm going to talk to you today about basically what's a portion of the output of my thesis, which I defended about, I guess, 6 or 7 weeks ago. very happy to be on the other side, but it was also a great journey, and I was able to explore, so not just bone conduction, but also some aspects of vibrotactile sensation. So thank you for inviting me here today. I will talk about my partners in my thesis just a little bit later. First, I want to just give a brief overview of how I'm going to give the presentation today. So starting with a little bit of the context, which Shelley began to discuss, followed by a little bit of background about vibratory perception, including, I refer to it as extratympanic conduction. I'll explain why. And followed up by the wearable device that I developed during the PhD. And finally, I'm just going to talk about one output, so one experimental output of my research, which is a study about bimodal judgment of auditory and tactile sensation. Finally, some little perspectives. So the context about why I am doing this research. So it's I'm glad that Pedro already gave his presentation, because we actually have quite a similar background in terms of the reasons for why we are interested in bone conduction and acoustic research. So I also have a hearing impairment since birth. It affects a certain range of frequencies, which happen to fall exactly in the range of the human voice. So I think since a very young age, it's made me actually more sensitive to sound and more appreciative of sound and its impact on my life. So I've also been playing piano since the age of 6 or 7, I don't remember. So I'm very passionate about music, and this passion combined with the curiosity about sound perception given to me by my handicap had made me ask for a very long time, like, what am I missing in comparison to what other people are experiencing, and what alternatives? And more globally, I think it's made me a more sensorially attuned person, also in terms of the sense of touch. So, personal context. Now I'm going to go into the precise research question, which guided my thesis. So I say precise, it's actually quite global. And it's what design and research methods will allow us to create and reflect on an alternative experience of sound, which involves the whole body. And then secondly, what tools do we need to probe the body's capacity to perceive and appreciate vibrations via the modalities of hearing and touch? So to put those questions into action, the goals of this project were to encourage and create an alternative sound experience, so not assistive nor substitute, by developing novel wearable technology, which you can kind of see in the corner of my screen. And the second goal, which is essentially the motto of the thesis, was to demonstrate that the experience of sound is really about the experience of vibrations, something that everybody can perceive and appreciate in their own way. So just to give a little bit of context about the ecosystem, so who I was doing this research with, it was research that I conducted with 2 laboratories. So one laboratory on the auditory end and one laboratory on the design end, so IRCAM and the Center for Design Research, NC Paris-Saclay. So I did this research in Paris. And on the tactile end, I was lucky enough to discover Vincent Hayward, who helped me get accepted into Actonica, who provided the industrial sponsorship of my research. So they provide basically everything that I needed to conduct this research on the tactile and auditory, but also industrial side of things, and they interact through the project. So in terms of vibratory perception, we've already gone over what bone conduction is, or extratympanic conduction, as I like to call it. I just want to speak briefly about frequency sensitivity in terms of auditory perception of vibration. So you all are probably already aware that the human ear, or a normal human ear, is capable of perceiving sound from 20 to 20,000 hertz. And also we can feel sound from 20 to 1,000 hertz. And so what I'm interested in my research is this audio-tactile sensory overlap zone, where essentially you can both hear and feel one same vibratory stimulus. And just to give some more context, these are the ranges of frequencies where music and speech are situated within these zones. So you can see that they all overlap. So we've already gone into what is bone conduction, cartilage conduction. I call it extratympanic conduction because it englobes everything that doesn't rely on the eardrum. So I won't go into detail about how it works in the ear, but I will go into detail about the fact that I did not focus on the skull in my research. I instead chose to focus on the possibility of ETC on the torso. And so I'm interested in this part of the body or parts of the body in my research for a few reasons. The first being that the torso presents musculoskeletal pathways to the inner ear for auditory perception, which I have validated in my research. And secondly, on the tactile end, the skin presents a canvas, what I see as a canvas for the spatialization of tactile effects and diverse vibratory perception. So we know that it's possible to hear and feel vibrations simultaneously via the same source signal. We already know a lot about tactile sensitivity. What we know a lot less about is auditory sensitivity via ETC on the torso, and even less about the perception of spatialized audio via ETC. So I'm going to go briefly over one device that actually enabled me to go a step further and create the wearable device. I'm not going to go too much into detail just in the interest of time, so we can return to this section during the Q&A if needed. So basically what I did to prepare for developing the multimodal harness was to develop something called the monopoint module, whose purpose was to analyze auditory perception of vibratory stimuli at several points in the torso, one by one. So the points of the torso that were interesting to me to then in the future implement in the wearable device. And then secondly, obviously there, to guide the next project steps of the wearable device and sensory effects development. So what does this module contain? There is one linear resonant actuator, also referred to as a voice coil actuator. There is a force sensor to measure the pressure against the body to make sure that's consistent at all the points we measured on the body. And there are 4 sticky hydrogel patches that stick onto the participant's body during the experiment. So what I essentially evaluated using this device was how does the ETC perception of a vibratory signal on the torso depend on that signal's frequency, amplitude, and position, with 2 hypotheses being that the auditory sensitivity will decrease with increasing distance from the inner ear, and that due to tactile sensation, certain frequencies thresholds will show an effect of cross-modal enhancement, or essentially the impact of tactile sensation on the perception of an auditory signal. And this study was inspired notably by these 2 references. So the method was essentially, I had the participants sit down. They wore earplugs and noise-canceling headphones, so they completely blocked their external air-conducted sound pathway. And I asked them one very simple question, which was, did you hear the signal? Except as it turns out, that question wasn't so simple, which I'll explain a little bit later. And I'm measuring here the auditory thresholds of detection with a specific psychophysical method, and I tested frequencies from 50 to 4,000 hertz. So the results essentially showed us that it is possible to perceive the signals through ETC at all of the positions we measured on the body, which you can see on the left-hand figure here. And so to interpret the figure on the right, what we learn is that here, so we have a higher sensitivity with a lower bar. So which means that we're seeing, as we are increasing in frequency, which are represented by the gradient of colors here, as we increase in frequency, we are decreasing in sensitivity at all of the positions. So what this here is showing us is that at 4,000 hertz, we have very high thresholds, so very low sensitivity, and around 100 to 440 hertz, we have very low thresholds or very high sensitivity. So what does this tell us? Essentially, we learned a few things, that again, all the targeted positions on the torso supported auditory perception. So we validated these positions for the next step of development. We also witnessed that we had essentially what's a cutoff for ETC perception on the torso. So we don't want to go above 2000 hertz. 4000 hertz was outside of the range of perceptibility. And then we have this most sensitive frequency range, which could potentially have been influenced by cross-modal enhancement, because the peak of tactile sensitivity on the skin is 250 hertz, and that frequency is right in between 100 and 440. All right, so now that we have this background, which is essentially serves as proof that it is possible to hear through the torso via ETC on these parts of the body, now I'm going to go into the multimodal harness, and I'm going to spin my screen so that you can look at it as I talk about it. So this is the wearable device that I developed during my research, and the goal here was to develop something that could transmit or spatialize the signals to several positions at once. So the goal of this device is not just to display vibrations, but also to encourage the user to revisit and maybe question their assumptions about sound perception, about how they can perceive sound. It has served as a tool for perceptual experimentation. And also it's embodied other creative and theoretical outputs that I'm not going to go into today, just in the interest of time, but if you want to check out my thesis, you can. So moving on, just briefly discussing how we built it and what went into it. So I worked with Actonica and a costume design studio called Les Vertugadins in Paris to develop this device, which involves two main axes of development. The first being the module, so of which there are 9 that we see along this, 5 along the spine, 2 on the ribs, and 2 on the clavicles, which are all integrated into the wearable structure. What you're looking at here that I'm touching right now, that's the second iteration. What you see on the screen is the first iteration. So there were some changes that involved. The main change was the change in the orientation of the actuator. Initially, we had implemented it horizontally or parallel to the surface of the body. We flipped that so that it would vibrate in the direction of the musculoskeletal structure. So this is what you see to my left. And this is the difference between the 2 iterations. So the device, it is one size fits all as much as we were able to. Essentially, it fits basically extra small to large. We weren't able to get everybody into the window, but we did the best we could. All right, so now that we understand what the background was before creating this device, the proof that we needed, very basic proof that we needed to be able to have enough reason to go ahead and create it. Now I'm going to talk about what it's allowed us to learn about audio-tactile perception. And this via one experiment, which is called bimodal judgment of audio-tactile stimuli. So in this experiment, our main question was, so when 2 modalities, hearing and touch, are stimulated at the same time by the same vibratory signal, how does one distinguish between them? Because this is actually something that evolved as we were conducting the first experiment, which was essentially, even though we were just asking the participants, do you hear the signal? Sometimes they would look at me and say, yeah, but I also feel it. And afterwards, after they had finished the experiment, they would tell me, I know that I was trying to answer the question whether or not I was hearing it, but sometimes I really wasn't sure if I was evaluating my tactile or auditory perception. So that confusion, I thought it was really interesting. And we purposefully excluded the tactile sense from our first experiment because we really wanted to just get that basis of ETC for this device. So now, once we had the device, we could look a little bit more into the details of how these 2 sensory modes overlap and how the different vibratory signal parameters affect our ability to basically pick apart our 2 perceptions that are happening simultaneously. So our hypothesis was based on frequency. So this is based on what we already know about auditory and tactile sensitivity. We know that tactile sensitivity ranges from 20 to 1000 hertz. we know, based on my previous experiment and one other that I didn't speak about today, that it is possible to perceive signals via ETC up to 2000 hertz on the torso. So given this sensitivity range that we knew was possible, this sensitivity range is not homogeneous in the sense that auditory sensitivity changes over this frequency range for bone conduction or for ETC. And tactile sensitivity, as frequency increases, sensitivity decreases. So we were wondering how that change in sensitivity reflects itself in our results. So with the expectation that with increasing frequency, perceptual judgments will shift from mostly tactile, I mostly felt it, to mostly auditory, I mostly heard it. So just a little bit of background, we used the multimodal harness as the instrument for audio-tactile perception. Again, participants' ears were both plugged and covered to ensure that there was no air-conducted hearing, and we conducted this test with 23 normal hearing participants. So, to present the procedure, the first step, which we thought was very important, was a calibration task, where on the left, we see this calibration tool that participants used to set the levels of intensity for the vibrations that were transmitted to their body at the 9 points that you can see on the figure on the right. So the 9 bars here each correspond to one position of stimulation on the harness. And then each calibration screen repeats itself 5 times for each tested frequency from 200 to 1200 hertz. So during this calibration task, we wanted to determine essentially the individualized equalizer for each participant. So what they would do is set the minimum and maximum levels, or maximum comfortable levels of intensity. And then we would take the median and use that as the amplitude during the next phase of the experiment. And they also had the possibility, if they had zero perception, neither audio nor tactile, they could cancel out certain positions for certain frequencies on the harness, and that was removed from the next part of the test. So, all right, we have this individualized equalizer, but what that means is that during the next part of the experiment, we can't draw any conclusions about the signal's amplitude on the averaged participant results because each participant would have a different amplitude. So what we also did was create a standardized equalizer, or a set of standardized amplitudes for each position and frequency combination, of which there are 45, 5 times 9. And we created this controlled amplitude value, which was calculated based on the pilot test results. There were 7 people who participated in the pilot test. So we averaged all of the medians of those 45 combinations and made sure that all of the amplitudes of those signals are higher than every participant's minimum. So every participant's threshold, essentially. So that means that this controlled amplitude or standardized equalizer is on general several times more intense than an individual person's individualized equalizer. So the bimodal judgment task, which involves this audio-tactile range that participants used to set their bimodal judgment, is what we call it. So essentially, in the procedure, you have a signal that's displayed to you. It says pure sine tone. And for each of those tones, perceived as vibrations or auditorily or both, they needed to rate the relative auditory versus tactile perception. And this can happen anywhere on this side, anywhere on this side. That is to say, it can be 100% audio, 0% tactile, or vice versa. The only thing that they cannot select is the 50-50 point, because they need to make a decision between, did I hear it more or did I feel it more? So we tested 200 to 1200 hertz, because 200 hertz is close to the peak of vibrotactile sensitivity, and 1200 hertz is just beyond the limit of tactile sensitivity. So the goal here was to have 2 poles, essentially, that would anchor the results and give this boundary where you have mostly tactile versus mostly auditory perception. And again, so the amplitude of the signal during this task is based on the calibration task. So the participants had both the individualized and the standardized equalizer amplitude values displayed to them during this task. So there were a total of 90 signals. So looking at the results, what do we see? So again, on the left, we just have the 9 positions of stimulation, just for a reminder. So what do we see on the graph on the right? So just to interpret the figure very basically, so on the y-axis, we have the audio tactile range, where -10 is 100% audio and 10 is 100% tactile. And 0 is this midline, where it's 50-50 or equal parts audio tactile. X-axis, we have the frequencies. So the data for, okay, that's a typo. It should say spine T. Sorry about that. What this data is showing us is that with increasing frequency, there is this shift that we see from mostly tactile to mostly auditory that we see across all participants for both of the equalizer's amplitude values. So we see this drop from tactile to auditory as expected. And what we can also see is that there are statistically significant differences between the bimodal judgments for both the EQS and the EQI for 200 versus 400 hertz and 400 versus 600 hertz. And then that statistical significance decreases between 600 and 800 hertz, and then there is no statistical significance between 800 and 1200 hertz. So looking at all right, get ready. There's going to be a lot of stuff on the screen. All right, so looking at all of the positions on the body. So not pictured here is we also ran a 3-way ANOVA analysis that showed that all 3 of the factors, so EQ, frequency, and position, had a significant effect on the participants' bimodal judgments. However, we cannot infer from this ANOVA which of the 3 factors had a stronger or weaker effect, because this would require a logistic regression that was a bit out of scope of the study. So what we see overall is a lot of things. So our hypothesis about frequency dependence was confirmed. We can see the transition from mostly tactile to mostly auditory. But what we see is kind of an interesting and unexpected result is what's happening around 400 hertz. So what we can see is that there is a significant difference in the distribution of bimodal judgments between 200 and 400 hertz and between 400 and 600 hertz at all the positions for both equalizers. So what this could suggest is that 400 hertz essentially serves as like a point of separation between mostly tactile and mostly auditory. And I'm saying this, it's not a generalized point of separation. It's based on the frequencies that we explored. It could be interesting in the future to explore more frequencies, but that is certainly a point of interest. And also, so beyond the effect of frequency alone, which I've been focusing on a lot, we can also see that there is a difference based on the position of stimulation and based on the EQ for the different positions of stimulation. So in terms of perspective, so moving on from this study, something that we didn't control, and which is admittedly a limitation in this study, is the effect of body mass or morphology, or in the same vein, the device fit on the individual. We did not control this. I basically put the device on each participant, told them to fill up their lungs. I tightened it as much as possible, and then they could breathe. It was more or less the same for each person, but it wasn't controlled. It could be interesting in future studies to use this similar bimodal judgment paradigm with another device or even other modalities. And finally, it could also be interesting, since we were unable in this study to separate the effect of each factor on the bimodal judgments, it could be interesting to do an in-depth evaluation of all three of these parameters. So that's it for me. Thank you so much for listening.
Thank you, Claire. Thank you so much. We already have some questions for you, so we could start with those, if that's all right.
Yeah.
We've got
There was also
here.
some stuff in the chat. People started writing in the chat first, but it's up to you.
We have, yeah,
Just
we
so
have
you
two
know.
sources of questions. Okay, so one from Renee. Claire, if you plug the ear during the test, don't you amplify the level of bone-borne sound occlusion effect?
So the occlusion effect, I did some reading about that, but I have to admit I'm not an expert. Basically, from my knowledge, is that the occlusion effect is dependent on frequency and that it concerns typically low frequencies. And since I'm working above 200 hertz, my estimation was that it shouldn't have too much of an effect in my study.
Pedro might know more.
Pedro might be able to help me on this point.
Pedro,
Go for it.
I didn't hear it. Sorry, what did you say?
I said Pedro may know more about the occlusion effect. Like
No,
how
I
much
was
of an
actually
effect-
thinking a lot
above.
about it, actually, while you were talking, because I'm wearing headphones. I was like, okay, let me just tap on my spine and see how much I hear it. And actually, it amplifies quite a bit when I'm occluding. So that was actually a question I had as well. But it's so you didn't consider the occlusion at all, also because when you if you add the noise canceling, then that also has some effect in the low frequencies. So I don't know. Yeah. So
yeah, so there was no noise canceling, no active noise canceling in my. Did I say noise canceling? I should have said noise. Just like
oh, okay, great.
I just meant like in like.
Okay, that's better.
Ear defenders
Ear
that
defenders.
block
I
out
don't know
sound.
how to call them.
Or, yeah.
Noise insulating. I don't know. Yeah. Okay.
No, there was
cool.
no active noise reduction.
That's great. That's great.
In terms of the occlusion effect, I am familiar with it and how it's been used in bone conduction studies to compare with and without. However, in the context of my research, I didn't get to go so far as to evaluate, because the reason why it was sort of a necessity in my project to use earplugs is because the amplitude values needed for ETC on the torso are much higher than those needed on the skull. And so if I wanted to have certainty that participants were not perceiving via air conducted sound perception, I needed those two layers of protection. So it was out of necessity, but it would be a really interesting point to evaluate.
Yeah. And I don't think it's necessarily a problem, because if everybody uses the same, then the variability might not be that much anyway, if it's a problem or if it's a phenomenon. But
if anything, cool. There would potentially be a relationship. I tried to teach every participant how to correctly roll their earplugs and correctly in their ears, but I can't control for that either. How deeply they were inserted. So
okay, so you put earplugs first and then you put the headphones. Oh, okay, I see. So, but that's better also. Yeah, cool.
Great. We have a question for. Okay, I can't remember Stefania's question. If it was for Claire or for the guys.
I think it was before me.
I think it
was.
Yeah, I think it was Gabriela's sound quality.
She's already asked me enough questions. She was on my PhD committee.
And I know Stefania's there with her students in the lab, so it may be one of the students who's asking. But let's take this one for Gabriela and Pedro. What does sound quality for a sine wave mean in your study? How do you interpret the difference in sound quality?
Yeah, that's a very good question. Basically, the idea we had in the study was focusing on the loudness and then trying to back up the results with the other measurements. So let's say during the presentation I was mentioning at some point, okay, we could be able to match the loudness of a certain reference down with bone conduction, but there might be some factors that, even though we match the loudness, are contributing to making that not sound very pleasant or very good sound quality. So we were trying to include some kind of measurement of, okay, how can we ask these assessors? Are they actually hearing something similar to what they would experience if they had like a full air conduction experience? And that's the way we found. In my opinion, this was like a limitation of the study. And that's based on the fact that we had to use untrained listeners, and because there were the conditions that we had at the time. The best way to evaluate this would probably have like run a study with people that are trained listeners that know how to spot the sound quality problems or artifacts, we could say, and then have like a full study running just on that. We didn't have time for it, but it would be super beneficial. And at that point, you could include even more bone conduction or cartilage conduction, as we talked about, devices and compare them. And that would probably be the best way to do it. So I was trying to include different perspectives in the same study. So yeah, I hope that answers the question.
I also want to add a point, because even though we have sound quality, the term is sound quality similarity. So it's not, because sound quality it can be perceived as something very, this is good sound, this is bad sound. But what we meant was how similar is this device's sound versus the reference device's sound. And so it doesn't necessarily mean that it sounds bad, because how can you tell it sounds bad or good? Because it just sounds different. How different? So I think it's an important point to add.
That makes sense. Question from Simon. Very interesting work. With the cartilage air path being dominant, aren't some of the advantages of the bone conduction? Headphones mentioned by Pedro may be less applicable in this case.
Okay, I think I'll just take this one. No, because everything I mentioned is applicable for both bone conduction and cartilage conduction. And I hope by that you mean the use cases and the skepticism. So all those things, they are applicable for both. In fact, when you play around, let's say you play around with a transducer and you're just going around in your head in different places, you can't really say what is one or the other. You can only say by the response. So especially, of course, if you know what you're doing, then you can definitely hear the difference in the response, but you can't really figure out, okay, this is more my bone and this is more my skin. So it really doesn't make a difference. They can be used in the same way, these technologies. It's more a matter of what results can you achieve with one versus the other. So with bone conduction, you would normally you would focus more on the skull. So for example, the Baha bone anchored hearing aid is a very good example, even though it's anchored, but meaning you have to drill a hole in the skull and go directly in there, and because the skin is seen as a damper. But then again, this is just another way of pushing sound in. So it's yeah, it just depends on what you want to do. But the advantages are pretty much the same.
On top of that, maybe, yeah, I can add quickly that there are different studies that have been trying to look into if the question was referring to the different contribution to cartilage conduction. So we had that slide with the three different, the cartilage bone, cartilage air, and the air kind of pure. So there are different studies. It's really difficult to find like an overall result of all of those added together, because each one is focusing on such a small detail, even creative ways. Like there was a study, they tried to fill the ear canal with water up to the bony part and just keep the cartilage part without any water, and trying to drive signal into that. Just to mentioning this, just to give you an idea of how many different things that we've been trying to investigate. So at the moment, it's really difficult to just sum up all these results and saying, okay, 30% is pure cartilage bone and 20% is this other contribution. So still, we do not have a final answer to this at the moment, I believe.
So now that you're working for Force Technology, you could perhaps set up a really nice evaluation listening panel with your in the Sense Lab there.
That could definitely be done.
That would be
that
nice,
could definitely
right?
be done.
Yeah.
Yeah.
I just want to add something to what you were saying as well, because there's a question here about comb filtering by René, and he's asking, so is there comb filtering between the different, between the cartilage and the bone, and how does all this cross propagation works? And again, it's very hard to know. I think right now is a lot of like testing and subjective just a lot of playing around and figure out. But I mean, from our experience, the way we do this sound stimulation, cartilage is definitely like the biggest contributor to get sound in. So you could say it's like 90, I'm just going to throw a number, but it's kind of like 90% cartilage and 10% everything else. So in that sense, maybe comp filtering, maybe it's not that big of an issue, but again, it's hard to tell. And I think we're still a little bit far away to have all these small nuances, all these differences figured out. I'm sure you also, Claire, in yours, like, how can you figure out all these things with so many transducers everywhere? And
Yeah, for sure.
yeah.
Okay, we have a bunch of questions here. One from Ronnie. This is interesting to me as a bass player. Some bassists nowadays on stage use a combination of in-ear monitors and an exciter plate that they stand on. I didn't know that. That way they feel the bass as well as hear it, so the excitation is via the feet. Just wondering if that excitation position could also give similar figures with respect to tactile versus hearing with respect to frequency.
Yeah, so that's a really thank you, Ronnie. So this is a really interesting question. I think in my research and also just in the design of the device itself, I limited myself to the torso. Partly based on the ease of developing a device that could integrate a bunch of different positions and the space of skin essentially that there is. So I didn't go any farther than the torso. I didn't look at the potential for bone conduction from the elbow, from the knees, from the feet. However, the feet have a much higher tactile sensitivity than the torso. So I can't answer your question as to how the tactile sensitivity could interact with ETC, because I'm not sure if the sound waves could propagate through the knees, through the hips, through the spinal column, all the way up to the inner ear. But if we're talking about using two source signals to evaluate the simultaneous perception, then that could be really interesting to look at that. Just gonna reread.
It would make it even harder to measure and evaluate, though, right?
Yeah.
another source.
But that's, I mean, I think this is the main, right? I think we all understand, like, the main reason why I feel that the connection between auditory and tactile sensation is so interesting, and so I think it's a passion for me is because of this connection to the experience of music, and not even just when you're at a concert and you're feeling the vibrations, but also when you're holding your instrument and the connection, the tactile connection that you have, not just with the physical instrument in your body, but also the vibrations that are coming from the instrument to your body. Like even like violin players, they're gonna connect their skull to the instrument and maybe have bone conduction of the sound in that way. So there's tons of interesting ways to think about that. Yeah.
Yeah, and it changes a lot depending on the room you're in as well. Like that's why maybe bass players need that extra input.
Totally. Yeah,
it's not the same at all as in their little tiny rehearsal space. Yeah. Okay, we got a few more questions here. Diego, does bone conduction transmission have any negative impact on the auditory system or health in general when having long-time expositions or high-level vibrations?
Do you want to go? Go ahead.
I can go.
Oh, go ahead.
Anybody.
Let's see.
Go for it. Go for it.
We all go.
So who's going?
I'll go. Okay.
Sorry, who's moderating this? Claire,
I could say, to the best of my knowledge, at the amplitude values that even I'm using for the multimodal harness, I would say there is no health risk. I would say you would have more of a health risk as for just being uncomfortable in such a tight device than as for any of the amplitude values of the vibrations. Mostly when vibrations get dangerous for the body and for nervous system damage, you're talking about using like hand tool, like heavy machinery, or you can have damage to your back and spine if you're sitting on really like construction vehicles all day long, every single day for months at a time.
Yeah.
Those are where the ISO like standards that you have to adhere to, that's where they come from. But there is no standard on superficial localized vibrotactile stimulation, and I think that needs to be done.
Yeah, I'm sure that's also a tricky one
Yeah.
to standardize.
Not sure, yeah.
Yeah, different bodies, different devices.
You want to
I
add
was gonna-
something, Gabriel? Because I want to add something as
Oh,
well.
sorry. Yes, go ahead.
But do you want to add something first? Go ahead. You look
Go
like
ahead.
you're...
Go ahead.
Okay. Yeah, no, I normally get this question the other way around, which is, oh, if I use bone conduction, does that mean that then I won't damage my ears? And I always go like, no, because normally the damage occurs at the inner part of the ear. So whether you go through the ear canal and the bones or you go through the skin and the skull, it doesn't really matter because the damage is at the end, not in the middle. So it's people always get a bit confused. So I would say that probably is the same danger as anything else. And if you think about the displacement, the physical displacement, maybe it's actually good that it can displace so that it's not, because when it's the air, the eardrum doesn't escape, it just goes. But when it's a vibration thing, maybe, I don't know, I'm just thinking physically, maybe it won't be able to propagate as high levels, but that's probably wrong. So I would say it's about the same, but it's we don't have any proof yet. So yeah.
Gabriella?
I think Pedro added all I wanted to
Okay.
add, so it's a pretty complete answer.
I have a health-related question. Have you ever considered using your harness in a therapeutic setting? Because I know that there's a lot of research about the vagus nerve and how we're all in fight or flight mode, and so because it's just where the vagus nerve runs from your skull down to your intestines. So have you considered to have it?
So that's
use it in that
really
way?
a fascinating question. I hadn't thought about the vagus nerve before, but something that I guess the way I can respond to the question is just by saying that a lot of people who've tested the device have made the comment about how it's very meditative. And I can also attest to myself, when you wear it, since you're kind of forced to listen with all of your listening power, since the signals are basically filtered by the body, it does bring sort of a like an inward focus on your body and yourself, and so it's kind of quite meditative. So I think there definitely is therapeutic potential also for this type of hearing, which would be, I guess it's more unique to this device than to ear-based or skull-based devices. But
Exactly. That would be
definitely
really interesting.
Yeah.
Okay. Niels, have you tried to measure the transfer function from the cartilage transducer input into a probe mic in the ear? For all therapists.
Okay, yeah. I believe this one's for me. And then he was adding just below, if the cartilage path is the dominant one, this could be an objective measure of the frequency response of the device and directly comparable to the frequency response of a traditional headphone. Yes and no, because I imagine this probe microphone to be inserted, let's say, very close to your tympanic membrane. And then we probably need to plug the ear canal to compensate for the direct air conduction contribution that we have by placing a vibration transducer close to the ear canal. So as you see there already, there are a couple of factors that might bias the measurement, because even if I plug my ear canal, my cartilage part of the ear canal is the most external one. So then again, just by plugging it, I might be reducing the vibration that I'm able to elicit from the vibration of the driver into the ear canal internally. So it's very difficult to compensate for all the different bias elements, the bias factors that we might introduce. So that's why people have been coming up with creative ways of trying to measure this, and because it's Like if we had like a perfect, you know, earplug that we could just put, you know, 1 millimeter and just plug the ear, that'd be amazing. But we don't have anything like that available, so that makes it quite tough to stop and to compensate for that sound getting into the ear canal externally.
I can add some stuff. I mean, I think I have to think a little bit more deeply about this, Niels. Maybe we can talk later. But I can tell you this. So what you're actually talking about now, Gabriele, because when you close your ear, like when you close it like this, if you close it like this, and if you close it like this, but if you keep on stimulating, but you close it, you actually you still get a lot of vibration. I mean, it keeps going, right? It's so what I'm trying to say is the air conduction is almost negligible. In fact, when you close the ear canal, you also change, you make the ear canal a resonator, so you also change the response, and it's really interesting to play around. So a probe mic, I would suspect that he means maybe an air conduction mic inside the ear canal. And if that's the case, I don't think that would be really useful, because if you can close it with the finger and everything is, I'm not sure this would be a way to do it. But yeah, testing the nonlinear characteristics, that could be interesting. I don't know how, but that could be interesting. But yeah, but maybe I don't know. I have to think about it.
Okay, and then one for Claire. I hope you don't mind that we're going over time.
I think it's fine for me, at least.
Okay, cool. For Claire, could you maybe elaborate on perspectives for generating perceptions based on presenting different signals simultaneously on different transducers?
Yeah, so I didn't go into this. Thank you for this question. I didn't go into this at all during my talk, but there was a whole creative component of my project where, which was essentially the reason for doing this experiment, so that we could know a little bit more about what type of perception we could elicit with the device to then put that into action for basically like a musical application, even though that is obviously not the only application that is imaginable with this device. So what we wanted to do was to essentially create trajectories of the signals across the surface of the body. And what we learned while we were experimenting with some initial max patches that we developed to create these signals and trajectories is that, so I was talking about like spatialized perception of audio via ETC a little bit earlier in the presentation. And what we learned is that it's basically impossible to have a spatial auditory component to ETC, because everything, even though you're perceiving it at a bunch of different positions on your torso, everything is being routed up through your cervical spine. It can't jump in midair from your clavicle to your inner ear if your ears are plugged. So basically spatial audio information is lost, but what's interesting is that then you have the tactile component to essentially fill in that information in the zone, in the range of frequencies where it's perceptible. So the goal of using different transducers simultaneously, it's again to create basically compositions for the body. So we worked, in a musical sense, we worked with a composer who used these interfaces that we created during the research and used these basic guidelines that we developed from the perceptual testing to then develop basically these études audiotactiles that work on a few different themes and that explore how the overlapping auditory and tactile perception can be used in a creative sense. And it's really hard to talk about it because I can't make you hear it. You have to be wearing the device, but I promise it's interesting. What the tactile component brings is making up for what the audio component lacks, because it's basically muffled. It's filtered by the body.
You haven't made it to Denmark yet, have you?
No.
You'll have to come to one of our
Yeah, that'd
If
be
it
cool.
passes inspection from, I don't know what they would think of something like
Oh,
that.
right, I see. Yeah. Like, is there a bomb in it? Might be an issue.
Promise it's not.
Yes,
Suicide
but
voucher. Like,
Can I add something to, I'm not sure this is relevant or exactly the same, but I had a chat with Vincent at some point and he was talking about perception of, like, for example, you can simulate things like feeling water because you have different sensors and you can do it in a way that it feels like you're in the water. Well, something like that. I mean, that's crazy just to think about it. So I think that's really cool. I mean,
yeah,
imagine,
totally.
yeah.
Yeah, I mean, that's actually one of the compositions that the composer made. That was the most frequent comment on the questionnaire after the demonstration. Sorry, my mind is in French.
All right.
Is that they thought that they were in a jacuzzi.
Right.
Because there were these like bubbling, like the sensations were moving from the bottom to the top, and then like,
Cool.
and they actually thought that it was supposed to be a simulation of a jacuzzi, but it wasn't. It was like a
Funny.
cosmic womb.
That's even better than vagus nerve stimulation.
It is. Do you have plans to further develop the harness or to sell it as a product?
So I am moving on to different horizons. I've been working on this project for about like 6 going on 7 years now. So I'm taking a step back. I'm still going to be like a collaborator, but we're hoping that there's a PhD student who has applied to do a thesis to continue the research. And then we're hoping to also re-invite the same composer in an artistic residency at Yakyam. So stay tuned.
Wow.
I would in an ideal world, I would have like 30 of these devices and be doing like group concerts and like and therapeutic explorations and stuff like that. But yeah, money.
That'd be amazing.
Mhm.
Money. Okay. Need to find some money. We'll look into that. There's one last question from Martina. Is there any wear and tear on the bone where the vibration is over time? I guess that's for Pedro and Gabriella.
I hope not. That's my answer. I mean, this is something that, how can you know? I mean, we're not there yet. But first of all, I mean, we're not even stimulating the bone. We're literally, we're doing this and my finger is the tragus. So the bone is not there. So no. But I can't tell for certain whether vibration doesn't have any effects on. I don't know. I think this is something that needs to be assessed over time, certainly. But also, go ahead. I was just wanted to say it probably has a lot to do also with the intensity. So if you don't do a lot of intensity, then and when you put it here, you can't create a lot of intensity. So I don't know how it works in other places, but yeah, go ahead.
I think I could make a comparison to the vibration that happens in your skull while you're talking, right? Like, I mean, part of what you're perceiving when you're perceiving your own voice is coming from the vibration that's propagated to your skull from the interior of your body. And is that more or less at the same amplitude? Is it damaging your bones? I don't know. That's an open question. Open.
I don't get the impression that it's enough energy to do damage.
Exactly.
It doesn't.
The volume is
right.
Yeah, quite small.
Yeah.
I agree. It's in the dosage, right?
Yeah. And I get nervous when my eardrums are, when something's too loud, I start to freak out a bit. So I don't have that impression at all.
That's so much more sensitive, right? It's just a thin skin of, that would burst before your bone wears off, I guess. I don't know.
Yeah.
It's still a very fascinating question. I mean, we don't know, like, these devices have not been around for such a long time. It could be like it could happen that maybe at some point your sensibility is slightly less. That could happen, and that could happen also in different parts of the body, but we just don't have data. And It's
Exactly.
it's also quite a difficult study to run.
Yeah.
To basically have someone with vibrations going for such a long time that then they can report some kind of difference. That's very
Exactly.
difficult to measure.
How much vibration are you gonna do until your bone changes? Yeah.
Well, I think we have answered all of the questions from the audience, and we've gone a little bit over time, so we should probably wrap it up for today. But this was really interesting and a great discussion, and yeah, I'm looking forward to hearing how your work continues and how your research continues, Claire. Please do stay in touch. And yeah, we'll send out the presentations and the recording will be online. So if you know someone who might be interested, please just forward it on to your colleagues and yeah, let them know about it. And see you soon for another webinar.
Thank you.
Thanks,
Thank you.
everyone.
Thank you,
Bye.
everyone.
Bye bye.
Bye bye.